Welcome everyone. Today we have the great pleasure to welcome Patrick Sebbah, who is a professor of physics at the Department of Ilan University since 2014. Patrick was previously a director of research at the Institut Langevin in Paris. He leads an experimental group mostly involved in light-matter interaction, mesoscopic optics, acoustics, and microwaves. Patrick's main research interest lies in strongly scattering, disordered media, and Anderson localization. His research in optics is focused on random lasers, non-Hermitian systems, in a project funded by the Israeli Science Foundation. He is also investigating magnetic photonic crystals in the microwave regime, a project supported by the US Air Force and the MetaMAT's. He is exploring transformation optics applied to chaos on curved surfaces and their counterpart in 2D, namely flat billiards with non-uniform refractive index. Patrick is also working on metamaterials for elastic waves, including flexural waves in structured elastic plates. His group published recently experimental results in transformed plates, as well as topological states steering in elastic plate. He is offering a postdoc position in his group for next year on related topics, so young people should definitely apply. And so today, Patrick will present some work on disordered systems and localization of elastic waves. Professor Sebbah.
Thank you, Sébastien. Good afternoon, or good morning, or good evening to everyone. That's the surprise with this way of interacting. I really want to thank Muammer, Bogdan, and Sébastien for organizing this meeting, this weekly meeting. I think it's a very nice format, as I was saying before, and you should keep it even after the COVID is finished. I think that's a very good idea to keep this format, and I think it attracts a lot of people and a lot of interest. So today, I would like to present not only work on disordered systems, but in general on structural systems. What I'm going to present here is essentially the experimental part of my presentation, but I will explain the theory, which is not our work, which is important to understand actually what we want to do and what we can do in such a system. So essentially, we are going to talk about flexural waves, or disordered systems in thin plates. And I will present this theory, which is called the landscape theory, which has been proposed a few years ago by Marcel Filoche and Svitlana May-Broda. And I will show you the power of this theory and how we can actually test it experimentally. So to start with, I will start with this short cartoon, which I think captures very well what I want to present to you today. So we have this happy guy who is back to his office after 1 year of COVID, and suddenly his table and equipment is shaking around him, and he turns around and discovers that the responsible guy is his colleague here behind him, and tell him that this is because of his jiggling of legs that everything is vibrating, his desk is resonating. So the guy apologizes, and then the guy has an idea and say, maybe you can adjust, you can shift the frequency by 15%, and this way we can get in resonance with Steve's desk instead of mine. And he gives the calculation, and the objective is to try to spill the drink of the colleague. So this is exactly the question: is what is written on this piece of paper? That's the theory we are looking for. How can we control the vibration in a vibrating system to localize the energy in a particular place in the room? Okay. So more generally, the concept of eigenmodes, eigenfrequency, and eigenmodes is an absolutely essential concept. It's a key ingredient to understand all the characteristics, the properties of vibratory system, This includes mechanical system, acoustical system, optical system. And we know that the knowledge of the eigen function is actually everything we need to describe this system, to describe the dynamic of this system, to understand, for instance, in disorder system, how they govern the transport. In a lasing system, how they will control the wavelength of emission, the threshold of the laser. In all cases, they are essential. However, in a number of systems, in many cases, their prediction is difficult. It's still a difficult problem. And we'd like to know how we can actually predict their spatial position, their distribution, their frequency. And I would like to present to you two examples where actually this question is difficult and is interesting actually. So the first case obviously is the case of a disordered system. In this particular case, we have a distribution of a random distribution of factors. And the question I ask you is what happens if I vibrate this system? Where will be the modes, what they will look like, what will be their frequencies? And it turns out that first it is strongly dependent on delta n, the index contrast of the system, and the position of the scatterers, but there is no indication of where they will appear. So for low contrast, you find that the modes are extended inside the system, and as you increase the index contrast between the scatterers and the matrix behind them, then you see that slowly the mode start to get trapped in a finite region of space, and at some point, the mode is fully localized within the boundary of the system. So the question is there any fictive boundary around this system that traps the mode? We don't see them in the distribution of the disorder. So is there a way we can predict the localization of this particular mode? So here I'm mentioning this celebrated regime on localization. So localization was predicted waves, and I show you here a nice example of an experiment that we the whole to inject actually the energy inside the system. And exploring the spectrum of this system, we discovered that actually that some modes are spatially localized, and this is the case here. And what is interesting here is that the mode is extended over a region, a finite region of space beyond the scatterers. So it's not localized by the scatterers. It can actually sneak between the scatterers, but it is spatially localized. And this is actually localization, Anderson localization, which is really a striking and puzzling manifestation of wave interferences. So another problem, which is completely different, is about here, the design of instruments. And I choose here in particular a string instrument, the piano, for instance. One of the masterpieces in this instrument, it was what is called the soundboard. So the soundboard is this wood board behind the bars here in the upright piano. In the grand piano, this is the board, the thin board that you see here, which is reproduced here. And you can see both faces of this board. And you see that we have actually ribs, stiffeners to straighten the plate. And the way it works is the following. So when you want to play a note, what you do is that you hit a key, which releases actually the system that blocks the hammer. The hammer hits for a very short time the string, which is vertical here, in that case here. So over a few milliseconds, actually, it hits the string. The string vibrates. The vibration is transmitted to the soundboard via the bridge here, because the string is attached to this bridge. So the transmission of the energy from the string to the board is done via the bridge. And then the board will radiate the sound to the audience. So, so actually, this is the masterpiece because it really gives the full volume, the full deepness of the full depth actually of the sound emitted by the piano. Okay? So what is interesting actually is that when you play a note, the note is not a pure tone, but it's a complex, tone, a mixture of sounds played by the string and by the soundboard. So that gives you the tone. It gives you also the timbre of the instrument that will make the difference between the piano and the guitar, for instance, or different type of pianos. And the question is how we can design this quality, the timbre of the instrument. And all the secret actually is in this design, in the design of these ribs, which are glued on the top of the soundboard. And this is revealed here by this experiment by Xavier Boutillon in simulation. He showed that actually he measured the first mode of the soundboard of the piano. So you see the first mode, second mode, third mode here. And what he found is that at low frequencies, obviously the structure on the soundboard, so the ribs and the bars here, they do not affect the profile of the mode. However, when you go to mid and high frequencies, then you start to see that the structure actually waveguides the modes themselves. Actually, they select the modes of vibration of the plates. So not all modes are allowed. There is a modal selection, which is played by this structure. So this structure is not simply here to stiffen the board, but it's actually here to give the quality, the timbre, the notes of the instruments. And to date, actually, when the board are manufactured, this is done essentially this is based essentially on tradition. There is no real tools to actually know how to place and to arrange the structure on the plate. So this is really a matter of expertise of these people and a matter of tradition also. So the question would be, can we actually think of a way to design this type of plate based on the physics of modes, of eigenmodes of the plates and the structure built on these plates? Those are other examples I show you here of string instruments, and you see clearly here the complex structuration of the plate with these stiffeners, which are essential to the quality, the tone of the instruments. But this is not limited to the design of instrument. It is also very important in the design of optical resonators, IQ resonators, chaotic resonators. We'd like to know actually how the modes are scattered inside the system. Laser cavities, this is very essential within the system that will help to design cavity laser, DFB laser, for instance, distributed laser or random lasers. A strong issue. Start the broad definition of a localized mode. So the definition is given here. So let's say that we consider a state to be localized if the amplitude of the vibration is large in a restricted region of the space. Okay, so this is very general. This is not necessarily Anderson localization, but it covers a broader range of questions, not only disordered system, but all the problem that I described before. And here are two examples. Those are quite interesting examples. Here you see what is called a fractal drum that was studied by Simon Felix and his group. And he showed here that the boundary here is fractal. You can have localization for particular frequencies of the energy at the edge of the system. That's another example here where you see that for the 12 mode, the 12 eigenfunction of this very specific vibrating system, the energy is fully localized in the top of the system here. And guess what is the title of this paper? The title was Localized Eigenfunction. Here you see them, there you don't. Okay, this is the basic definition for localization. So this is interesting for many reasons, specifically for application. This is interesting for structural engineering, control of vibration. When you want to design walls that block noise abatement walls, musical instrument design. And there is an interesting problem that I want to show you now, which is the clamp plate problem. This is a very simple problem that was addressed by Marcel and Zvitana, which is the following. So let's consider a rectangular plate. Okay, we know the mode of such a plate. And let's clamp it on one point here. Okay. What they showed is that if the eccentricity square root of here is large enough, almost all the modes are localized either on the right side of the plate or on the left side, this blue region here. So you see one example here, another one which is localized on the left side, another one here, and almost all of them are either on the right or on the left of the plates. But you agree that there is no frontier here, there is no barrier that blocks the mode, only one clamp point. Okay, so there is some kind of fictive boundary that we would like actually to guess. In that case, we can guess it because of the symmetry of the system. But in a more complex geometry, we'd like to be able to guess the fictive potential that trap the mode within it. So the questions are summarized here. Is there an effective potential that traps the wave, the mode inside the particular system, even if it is very complex systems such as a disordered system? Can we guess what are the invisible confining boundaries in such a system? So we need some kind of tool, some kind of predictive tool to be able to guess what will be the spatial and spectral properties of the modes. And we want to avoid, obviously, the brute force method, which is the eigenfunction solver using COMSOL or other system, you know. And we'd like to be able to predict actually the frequency dependence of these modes, how they extend, how they distribute within the system. And the last but not the least will be the inverse problem, as it is the case for the design of for music instruments. Can we engineer plates with particular vibrational properties? How can we design them to select particular sound, particular resonances within the plates? So to address this question, Marcel and Zvitana propose a very nice theory, which is the localization landscape theory, which is a new theoretical tool that can retrieve all the crucial information on the localized mode in a particular system without actually knowing the microscopic structure of the system. And that's the key element of this theory. So let me describe it very briefly. Let's consider a given operator L. L can be the Hamiltonian, if this is the case, if we are in the case of the Schrödinger equation, it can be the Laplacian for the wave, the Helmholtz equation. It can be the Laplacian squared if we consider the Helmholtz law equation for plates. In all cases, we know that the properties of the system are completely described by the eigenfunction and the eigenvalues, which are given by the eigen equation here. L phi is equal to lambda phi, okay? As long as we define a boundary condition here, for instance, a directly boundary condition, okay? So this is the standard eigen problem to solve. So the proposition is the following. For any point in space, one particular eigenfunction will be bounded by the eigenvalue times the function u. This function u is the solution of the directly boundary problem. Very simple problem. Lu is equal to 1. So you see here that the right-hand side element here is a constant 1, and actually u is directly given by this expression where g is the green function, and this is a 2-line demonstration. They really bluff the mathematician because it is extremely simple to demonstrate, and this is this function u that we call the landscape function. So concretely, what is this function? If you want to solve this equation in an experiment, what you would do actually is to apply the static deformation on your given system, and actually plot the deformation of the system under this static deformation. And what you get is this u function, which is called the landscape function. This is actually a landscape with valleys and peaks and hills, okay? And this landscape actually will partition the domain, will partition the space into subregions. These subdomains will correspond to the localization region of the different modes. Actually, this is what is meant by this expression here. You see that when u is small, the eigenfunction must be small too, okay? It is normalized to 1 here, so it must be small. That means that the function u actually gives you the partition of the space where the mode will be localized. So let's try this theory for the simple case of the rectangular plate with 1 clamp point. So in this case, for different value of the eccentricity here, we can compute. So this is not a mode, this is the computation of the landscape function u, okay? You see that as E increases, you see that slowly but surely there are 2 domains, 2 hills that appear in this landscape, okay, separated by a line here, a valley, and this valley actually determine 2 regions of localization, and that explains why the mode were localized either on the left side, on the right side of the plate. Okay, so that's a very nice illustration of it. We are going to explore more complex system, and I will show you actually how powerful this theory. So to summarize here, the landscape theory actually describes the subregion of localization of the system. They give actually in a single measurement, just applying a static deformation. It can give actually the eigenfrequencies of the mode, the eigenmode profile, and the frequency dependence of the spatial distribution of the mode. Remember, this is a static measurement, which gives a precise, which actually, this is very interesting, by the way. I mean, it's the static measurement, which give information about all the modes inside the system. And once you get the mode, you get the dynamic of your system, because any field distribution can be described in time and space as a linear combination of the eigenmode of the system. So this is a big surprise. I mean, just a static measurement gives you access to the dynamic of your system. And this is done without any knowledge of the microscopic structure of the system. And thanks to this model, actually, thanks to this theory, we can address the inverse problem and assuming a given landscape, we can actually design the system geometry which corresponds to this particular landscape, giving the distribution of to obtain in a particular system. The power of this theory and what is expected by this theory, and our goal here is to demonstrate actually experimentally this system. So here is, after this long introduction, here is the outline of my talk. In the first part, I will show you the case of a structure plate where we can confine energy. So this is a kind of quite simple system And I will show you that we can actually measure the landscape in this system, and we can predict where the mode will be localized within my presentation. I will address the case of disordered system, and I will try to show you that actually we can localize mode by disorder in a randomly pin plate, and we can actually calculate the landscape and show where the mode are expected to be localized. So we are going to treat two cases, the pin plate and a system which is the random distribution of blind holes in a thin plates. Okay, so let me start. Let me first take a small break to thank my collaborators, so Marcel, Philoche, and Svitana Mayborda for the theoretical part. Michael Atlan for the instrument that will be used to measure actually not only the mode but also the landscape of localization. I would like to thank my postdoc, Gauthier, Kuhn, and Etam, who recently joined the group, PhD student Olivier and Marc, and a group of happy students to develop. So the part one, try to confine the energy and to understand how this is. So the structure is the following. Plates. We are going to carve a region which has a L here in the plates. Okay, so this structure, as it, the mode will be localized. All the boundaries will be clamped. Okay, and the structure that we design is the following. This is an exploded view of it. So the plate which is here is clamped between two frames, here at the base and here an empty frame. And you see that we can arrange actually these screws thanks to this network of holes here, to this grid of holes, to clamp the plate not only in the L shape, but also here and at these 2 points. So here we are going to explore the vibration of this plate. We are going to consider the vertical displacement, okay, so the antisymmetric mode of the Lamb waves. And we are going to consider the low frequency regime, so flexural waves of this plate, which are nicely described by the Kirchhoff law equation, so the double Laplacian delta squared. Okay. So here E is the Young modulus and nu is the Poisson ratio, rho is the density, and h is the thickness of the plate. This is the setup that has been designed by Michael Atlan at Institut Langevin, which is based on an heterodyne holographic imaging system. It's actually, I will not go into details here, but you see that a vibrating plate reflects actually the light. So the light is modulated, shifted in frequency, okay? And actually by double heterodyne of the system, he ran to get actually amplitude and phase of the full image. Actually, we can image the full system in one measurement, the mode. So we actually sweep frequency slowly, and at some point we observe a particular mode of the system. Later on, for a higher frequency, in a second mode, third mode, fourth, etc. So here we have 8 modes of the system that are directly imaged as we scan frequency. So some of those modes are localized at low frequency, and at higher frequency, you see that are extending inside the system. So the objective here is, first, can we measure the localization landscape in this system? Second, can we apply the theory of the landscape to predict the position of the mode, to predict their eigenfrequency, their resonant frequency, and maybe more than that in this system. So how can we measure the landscape? Actually, this is the way we proceed. We actually attach the system on a larger plate here. We try to make it as hermetic as possible. And by using a pump, a vacuum pump here, we actually apply vacuum inside the system to actually reduce the pressure as much as we can to deform the plate. So you see that the plate will be deformed everywhere where it is not clamped. Okay? And this deformation is exactly what we want. We want a static deformation of the plate. So if we can actually measure this deformation, we get directly the landscape for this particular structure. So to measure it, actually, we use an holographic interferometry setup. We are going to measure simply the phase. What happens is that the system is not fully hermetic, so we applied vacuum with the pump. We stop the pump, and after some time, the pressure is released, and the low pressure is released, and the plate goes back to its steady state position. Okay, so we can measure actually the evolution of the phase over the plate, and we can accumulate the phase to retrieve the initial deformation of the plate. And this is shown here. You see, as the pressure is released, we accumulate the phase inside the system, and appears a landscape, which is shown here, actually, which describe the landscape, the U function that I explained before, which correspond to our structure here. Okay, so this is its view from the top, and what we can draw here is the line of steepest ascent and steepest here. This is the profile of the you choose. So if you consider of a plate, you consider a membrane. So here it's not the signal operation and the scalar wave that is applied. You see that the landscape contrast to our case, we are dealing with flexural waves with a metallic plate. Okay, so elastic waves, and here and give us 4 regions of localization. Okay, so this is very important because it's really a signature of the nature of the operator, which govern the system, not only the boundary conditions. So if I move forward, let's see. Let's compare now the localization landscape with the mode that we found. So this is the first mode that was found, and you see that indeed it is localized in this region defined by the landscape. This is the simulation here, this is the experiment. Second mode here, localized in the second region of the system. Okay, so we can actually follow all the modes within the system and show that they are localized in the region defined by the landscape. And that's actually the confirmation of the theory. The eigenmode of the system are bounded by the low value of U. Okay, so those lines, those white lines, which correspond to the Valet of the landscape. So the eigenmode are small, where U is small, and that defines actually the valleys, and which are these famous fictive is given by the localization landscape. Second interesting prediction by the theory is that we can predict actually the position, not only the position, but we can predict also the frequency of the mode. And this is given actually by the height of the hills. So if you measure the height of the hills, the maximum of U in different regions of the system, actually this height is related via a coefficient to the inverse of the square of the frequency of the mode. That's given by the theory, and we can test it in our system. And indeed, which we show with quite good agreement that the maximum deformation, given here in microns here, is directly related to the frequency of the mode corresponding to the different regions. Okay, and you see that it fits actually the theory here given by this equation. So here we have a second prediction, not only the position, but also the frequency of the mode as we scan frequency within the system. There is a third bonus given by the theory, and it's a very important one. Remember the condition here, that's the proposition that defines the U function, the landscape function. Now, you should note that because the wave function is normalized in this expression, this condition, this constraint is relevant only if this expression here, lambda times U, is less than 1. Otherwise, there is no constraint because this is already normalized to 1. Okay. Because of that, there is a condition on U, which is given by U, should be less than 1 over the frequency of the mode, the eigenfrequency of the mode. Okay. So this gives you a condition. This is what is referred as the effective Valet network. Not always is the U function useful, actually. Depends actually on the value of the frequency. So U is uniquely defined, but the Valet network, it will evolve as you increase the frequency of the system. Okay, because this condition must be fulfilled. And I show you here in this quick movie. So we increase frequency, and as we increase frequency, we have this new condition that actually reduce or saturates the landscape, and you see that actually the lines of the valleys are cut. Okay, so actually they open, and while they open, they will allow larger mode to vibrate inside the system, mode that occupy a larger space of the system. And this is demonstrated in the experiment here. So that's the first mode, low frequency. The valleys are closed, okay. A gap that appears in the Valet network. We can actually expect to have a mode extended over the whole system here, and here it comes. You see this mode, which actually occupies a region beyond the initial valleys of the landscape. So the Valet network gives you the actual region of localization, and as we increase the frequency, the valleys open more and more, and we can actually predict the region of where the mode will extend actually. Okay, so this is a very interesting prediction, which is confirmed by the experiment here, that the system, as you increase frequency, the mode will extend within the system, and we know where they will extend. So to summarize the results here, so the localization landscape describes the subregion of localization. The local maxima of the localization of the landscape region actually provide with the eigenvalues of the modes. And we saw that the Valet network gives actually the frequency at which gap will open within the system and mode will extend inside the system. So just a word about the reverse problem. And the question is the following. That was the question that was asked group of students. Can we have actually a X-shaped vibration within a plate, a clamp plate like this one? So the question is, if I give you a limited amount of pins, can you place these pins to force the system to vibrate in an X shape? So the procedure is the following. You define the target function at the X shape here. You place your pins inside the system. You measure the new landscape, okay, and then you iterate and try to minimize this landscape with the landscape that we would like to achieve. And this is the result with 16 pins. As we increase frequency inside the system, you see the experiment in live. You see the X shape that appears for particular frequency. As long as it's not too high frequencies, when it's too high, then the system spread over the whole plate because the Valet network opens completely within the system. So here are some snapshots where you see the X obtained for 60 pins. Okay, so this is a simple example, okay, but I think it is very interesting and instructive as far as we can go with the inverse problem and how we can use the theory of the landscape to design any type of vibrating system, including musical instruments. So here we have the first experiment validation of the theory of the landscape localization. We actually measure directly the landscape. We show that we get most essential information about the modes inside the system. All these in a single static measurement, which give actually the full picture of the system, almost the full picture of the system. And more than that, we show how the system evolves as the Valet landscape develop inside the system. So I don't have much time. I would like to switch now to the disordered system. And I would like to show actually the result that we have in two different systems. So the motivation here, I think it's very interesting to be able to predict localized states in a particular system. First, because we don't know much actually about Anderson localized mode, especially in 2D system. We'd like to observe them, to study their interaction, their coupling. We would like actually to understand also the transition from localized to extended state in this system. And we'd like also to investigate the dynamic of the localization. One interesting application would be obviously to trap the energy, to be able to confine the energy in the system, to control it, to actually apply that to absorb the energy within a particular system, to reduce the noise, control the vibrations. And beyond that, it would be interesting to be able to predict localization state and to engineer the structure for different applications, especially for laser design, random laser designs. So the first experiment has been tried some time ago to observe localization in a thin plate. And the plate here is described. This is actually a silicon wafer, which is perforated randomly. So we are through does not achieve. So obviously such a thing was not strongly capturing enough to reach the regime of localization. So we propose routes, two possible routes. The first one is to consider a pin plate, and this here I will discuss first. Show you some results. So let's start with random plate. The screen is shown here. Design in a plate which is 33 by 33 centimeters. We have 100 pins here, which are electromagnet. So this system is strongly clamped. The system can be actually put in the vacuum chamber to reduce, or not eliminate, but at least to reduce radiation in air. And the system, the measurement system, is simply a laser vibrometer that scans the plates to measure the vertical displacement as we excite the plates. A transducer to vibrate the system. The interest here is that we are in the time domain. We can fully transform and measure the mode inside the system. So this is a particular measurement. I think this is the first mode that we obtain as we increase the frequency. So we can imagine that starting from 0 frequency, you will not find any mode until you reach some kind of cutoff when the wavelength is small enough to be trapped within the scatterers. So you see that it's not simply here, but it extends in the side. Actually, if we look on the log scale at the intensity of the mode, you see clearly that the mode is extended beyond the scatterers, beyond the pin points. Okay, so this is one mode. We can compare that to actually simulation. So we have very good agreement with simulation. And what we see better on the log scale in the simulation is that as you go away from the center of the mode, you see that the color changes like by steps. Okay, so we have like circular region with different colors, which show actually clearly that we have an exponential decay of the intensity of the mode within the system. So here are other examples at higher frequency. You see that the mode can extend further. So as we increase frequency, the mode extend within the system. And you see clearly that they are exponentially localized inside the system. So let me show you, I'm going to scan frequencies here. This is only the simulation, but I'm going to scan frequency to show you how the mode, the actual eigenmode, explore the full system. So they seem to be trapped between the scatterers, but at some point they will expand beyond the scatterers, as you can see here. So we can actually reach larger mode. And you see how, as we increase frequency, so this is a very interesting system where actually for low frequencies, you are strongly localized, strongly confined. And as you increase frequency, as you see here, the extension, which is represented here by the inverse participation ratio, the extension of the mode increases within the system until it reaches the limit of the system. So this is an interesting system. And the question is, what can we do? How can we do any prediction using the landscape theory of localization? So here we computed the landscape, and it is shown here. So you see region with hills, region with valleys around the scatterers, and the lines here show again the lines of steepest ascent and descent along the landscape here. So again, you remember LU is 1, so this is the solution of this equation. We expect U to describe the region of localization of the system. U correspond to the static deformation of the system itself, and it will delimit the valleys and the region of localization. So here we compare the measurement in our system with the Valet network, and you see that indeed we are localized in this. So those are not modes. This is the landscape again. Okay, this is the result of the static measurement. It's not a measurement here; it's a simulation, but it's a static deformation. Okay, and you see clearly that the mode is localized in this region. As we increase frequency, we explore other modes, and you see that they're always localized within the limited region by the lines here. And you see, I'm going to explore that further here. The second prediction of the theory is actually that the modes, the frequency of the mode is given by the height of the hills. And you see a very good agreement here with the theory, even better than in the previous case. So we can actually predict the frequencies for the mode that will be excited in a particular region of the landscape. So here, I show you a superposition of the landscape valleys and the mode of vibration as a frequency is increased inside the system. And you see at the same time, you will see, yes, you can see it in this region here, you see as we increase frequency how the landscape opens gaps. And at some point, this region will be available for a new mode. You see the mode is here. This mode now can actually fit perfectly in this region of the landscape, while it could not do that while it was closed here. So we see the perfect adequation between the landscape and the mode that we measure inside the system. If you look on the low scale here, we can actually show that it's not intensity, but actually the intensity of the mode decreases by steps. When you jump from one region of the landscape to the next one, you decrease by one step, actually by an order of magnitude. Each time you enter a new region, and this is better shown here, where we show the log of the gradient of the wave function compared to the landscape valleys. And I mean, the agreement is perfect between the two. So in summary, I showed you that we can actually first localize state within a pin plate. I showed you that the extension of the mode increases with frequency in this system. And I show you how the landscape theory is perfectly demonstrated here. They describe perfectly the eigenmodes, not only their spatial location, but also their eigenvalues. They give a position, eigenvalue, and they show you also how they evolve as the landscape breaks as frequency increases. Next, that's what we are working on now, is really to measure directly the landscape. So we design a slightly different system. Actually, the plate is now the cover of a vacuum chamber. Okay, and as you make vacuum, you pump the system. You actually press the plate on this forest of rods that will clamp the plate randomly inside the system. And we expect actually both to measure directly the landscape in the system and the mode in the system. So we expect really to have a direct measurement of the landscape in the disordered system. And I will finish rapidly in the few minutes that are left to show you a different system, maybe a more challenging system, which is, oops, what happened? Sorry. Something happened here. Are you still with me? Hello?
Yes.
Yes, we are.
You know what? I don't know. Okay, my PowerPoint crashed for some reason. I'm sorry for that. Maybe because it's the end of my talk, I don't know. Let me go over it rapidly in a few minutes. I'll be fast.
Beautiful landscape, by the way.
Yes, that's a very nice illustration of the Alps. Okay, so back on my presentation. 5. Okay. Okay, I can continue rapidly. So I mentioned to you this experiment using through holes. Actually, what we did is slightly different. What we are going to use here is a blind hole. So actually, we have here not a passive scatterer, but a resonator. Actually, this part of the hole, the back of the hole, is a vibrating membrane. Like it works as a vibrating membrane, and you can see here from the calculation from the experiment that we have modes very well defined, okay, which correspond to the various mode of vibration of the lower part of the hole here. Okay, so by playing on this resonance, actually we can design a disordered system, and this is the system that we design, which is a system with more than 300 holes, blind holes, randomly distributed. So this is a kind of silicon wafer. It's a silicon on insulator wafer that we design to have holes with exactly the same height, because the resonance is very sensitive the height and this thickness actually, to the thickness to be here. So we have to be extremely careful to have a uniform, an homogeneous type of disorder. This is the experiment where we use an heterodyne laser interferometer to make the measurement in a vacuum chamber, shown here. Excitation is done also by a pulsed Hini laser. This is actually what we measure. I wanted to show you something different, but that's it. Okay, so what we measure actually is actually the dispersion diagram that we can actually recover from this measurement. What you see clearly here is the dispersion relation of the antisymmetric A0 mode, but you see that at two particular frequencies here, we open gaps. And actually they correspond to the two resonances of the holes. They are called hybridization gap because they're related to resonances, okay? And if you zoom on this gap, what you see actually is a forest of, many modes actually. And we're going to explore these four particular modes. We have the red one here, the green one, which lies at the edge of the gap. And we have the black symbols here. We are away from the gap. And what you discover when you actually look at the measurement of the modes for the black symbols, modes are extended within the system. Now, if you image the mode for the red and the green symbol, what you observe is that the mode we see here actually is the intensity of the mode at the actually inside the holes. This is actually the dimension of the plate. Okay, so we are really localized within the system. And if you zoom in, you see that not only that the energy is localized within the holes, but it's also localized in between the holes. And we discover two types of mode for the red and the green. You see that the green mode here corresponds to energy plus and minus out of phase between holes, while in the red mode, all the holes are in phase, actually. They oscillate in phase, since K vector is small on this side and high on this side. So we find actually two types of modes in this system. We can calculate actually the localization length, and we show very nicely that these the blue curves here. We show actually the localization length as a dip here near the resonance of the hole. Okay, and this corresponds to the theory very nicely of the localization length within the system. So to summarize, I was fast on this section, but I think it captures essentially the main result. I wanted to show you that by using resonance scattering, we can actually observe localization. This is demonstrated here in this thin plate with blind holes. Localization length can be measured, and we show a minimum near the resonance of the blind holes. And we find actually two types of localized mode, which are identified on both sides of the hybridization gap. To conclude my presentation here, we have demonstrated that we can confine energy, confine modes, localize them in two different situations. First case is the pin plate, the randomly pin plate, and the second one is the localized system with resonance scatterers. They correspond to two different situations. In the first case, actually, we have modes which are trapped between inside microcavities within the system. And I show that as you increase frequency, you increase the extension of the mode, while in the second system, off resonance, we have with scattering, mode are extended, where at resonance, we have strongly confined wave function in the system. I show you that the landscape theory of localization can be applied in the first case, okay? The question left is, there is no theory at this point to describe a system like the second one, where we have resonance scatterers. This is not included yet in the theory. I know that they are working hard on that. Maybe they already have a solution, but at this point, there is no landscape theory that can predict the mode in the second system that I presented. So with that, I would like to thank you for your attention, and I'm open for questions. Thank you very much.
Thank you very much, Patrick. It was a wonderful talk. So please come forward with your questions.